I wish to welcome you to today's ECT STAR introductory colloquium on the science topics of the workshop Relativistic Fermions in Flatland, Theory and Applications. This workshop was planned originally for 2020, but has been deferred to 2021 because of the COVID-19 pandemic. It will focus on strongly coupled planar fermions in layers of condensed matter systems, providing potentially new insights into QCD matter. As you know, the intention of this colloquium series is to introduce and publicize the science case of the workshop to a wider audience. Today's presentation will be given by Lukas Janssen, who currently heads an EMERGENCE junior research group funded by DFG at the Technical University in Dresden. In 2012, he received his PhD from the University of Jena, together with Holger Gies. From 2013 to 2015, he was a postdoc at Simon Fraser University in Canada, and from 2015 to 2019 at the TU in Dresden. His main research interests are in strongly correlated quantum materials and field theory aspects of condensed matter in general. Lukas, thank you for agreeing to give this talk.
Let me start by thanking the ECT STAR for suggesting this format and also for giving me the opportunity to present here. In this talk, I'm going to discuss emergent phenomena in quantum systems of many particles. The focus of this talk will also be the focus of the forthcoming workshop taking place next year at ECT STAR, hopefully, and it's about Flatland fermions. So fermions in two spatial dimensions. This is, of course, a topic that was intensely studied in our community, often with a motivation to kind of find analogies to things that are similar to high energy physics, and in the end, ultimately, maybe to understand effects of high energy physics. Today, actually, my focus will be a little bit different, and I will argue that, in fact, these systems are worth to be studied on their own rights because they show very interesting, new, and I think fascinating physics that can emerge in such systems. I will argue that these systems host intriguing quantum phenomena, such phenomena which have, so far at least, no analogies in other parts of physics. So this is what you can expect today. I will start by motivating the idea of emergence. And I will argue that, in fact, condensed matter is much more than just applied quantum mechanics, just as nuclear physics is much more than just applied particle physics. I will then substantiate this claim by discussing three examples of emergent phenomena. I will review the emergent Lorentz symmetry that we believe is taking place in systems like graphene. And then I will move on to materials that can realize a non-trivial topology. And I will discuss how relativistic Flatland fermions, if you like, can emerge on the surface of such a topological system, a topological insulator. Then, lastly, I will move on to the maybe most intriguing part. I will argue that new types of particles, emergent excitations, can arise from a mechanism that we call a fractionalization. I will discuss a purely bosonic model with, however, strong interactions, and I will argue that in such a model, fermionic excitations can arise at low energies, and even fermionic quantum critical points, something like a fractionalized version of the system that we very well know in graphene can arise in such a system. It is sometimes said that the fields of science can be arranged by their alleged purity. In that sense, because sociology is the study of the behavior of many humans, that of course follows from the behavior of individuals, which are studied in psychology. It seems very natural to conclude from this fact that sociology is just applied psychology, which then one would then argue that psychology is then just applied biology in the same sense, which is just applied chemistry, which is just applied physics. It's really nice to be on top. As scientists, of course, we assume that ultimately everything is controlled by the same set of fundamental laws, and we seek to find those fundamental laws. But does from this fact really follow that the only scientists that study anything fundamental are those that are working on those fundamental laws? There is in fact a problem with this point of view, and this is related to the issue of complexity. The fact that everything reduces to simple fundamental laws does not imply the ability to start from those fundamental laws and reconstruct the universe. In simple terms, just because I assume more or less all of us know more or less the physics of every screw and wheel and bumper of a car, this fact, that doesn't mean that we as physicists are able to reconstruct such a car from its 30,000 constituents. This is of course an observation that was made already a long time ago. The whole is greater than the sum of its parts. This quote is attributed to Aristotle living the 4th century before Christ. More recently, Phil Anderson has put it into a simple 3-word formula: more is different. This is something that we know very well from everyday life. The fact that the market values of the 3 strikers of PSG exceed those of the whole Bayern team considerably, this fact didn't lead to a single goal in this year's Champions League final. Obviously, the value of a soccer team is far greater than the sum of its players' transfer fees. Also, in information technology, companies like Google, Amazon, Facebook, or SAP in Germany, they collect huge amounts of data because they know that combining such data allows to extract implicit information that goes far beyond the explicit information that is collected. And lastly, life itself certainly is much greater than just a conglomerate of carbon, hydrogen, and nitrogen atoms and the compounds that can be constructed out of those atoms. Therefore, sociology is not just applied psychology. Biology is not just applied chemistry. And condensed matter physics is not just applied particle physics. At each field, entirely new laws, concepts, and generalizations are necessary. And those concepts require inspiration and creativity to just as great a degree as in all the other fields. In this talk, I'm going to discuss 3 instances of such new concepts for the examples of condensed matter systems. So let me start by discussing the emergence of relativistic symmetry Lorentz invariants in systems that are from the outside actually non-relativistic. Consider graphene. Graphene is a 2-dimensional sheet of carbon atoms, and this 2-dimensional sheet is actually very well modeled by assuming just hopping electrons on a side of the lattice. It's a honeycomb lattice, so we have hopping electrons on the honeycomb lattice. In the half-filled case, because this hopping then is perfectly allowed and without any interactions, there's no energy barrier. This is a material that is electrically conducting. The band structure consists, however, of linear band crossing points, 2 linear band crossing points in the first Brion zone. In the clean, that is undoped case, the Fermi level is precisely at these crossing points in the half-filled case. So that means that at low energy, the excitation spectrum is described by massless, the dispersion relation of massless Dirac fermions. At low energy, therefore, the physics is completely described by the Dirac equation without any external mass. At low energy, therefore, we have a new symmetry that emerges out of this non-relativistic system, emergent Lorentz symmetry. It arises from the constituents, although those constituents are fully described just by non-relativistic many-body quantum mechanics, Schrödinger equation, if you like. Now, what happens if we include interactions? Consider for simplicity just on-site Coulomb repulsion. So that is, in a sense, this Hubbard U that gives an energy barrier for 2 electrons sitting on the same site. If U is not large, then fermions can hop from one site to another, and therefore the ground state is described by a semi-metal. It's a semi-metal phase with the low energy excitations being itinerant Dirac fermions. So it's a Dirac semi-metal. However, if U becomes large, then this energy barrier that gives cost to 2 electrons sitting on the same site, that forbids the hopping, and in the half-filled case, the electrons will be fully localized with each electron sitting on one side of this honeycomb lattice. So the ground state will be an insulating state, a Mott insulator. The remaining degrees of freedom in this Mott insulating states are just the spin degrees of freedom. So the rotation of this arrow, if you like. So the ground state is a magnetic insulator because we have still magnetic degrees of freedom. And at very low temperatures, those magnetic degrees of freedom will order. We will have some type of magnetic order, and usually in this Hubbard model, this will be some antiferromagnetic order with spins on neighboring sites pointing in opposite direction. This antiferromagnetic order spontaneously breaks rotational symmetry in spin space, so it's a spontaneously symmetry broken state. So here we have 2 different phases as a function of U, and they are distinguished by symmetry, and therefore it's impossible to adiabatically go from one side to another without going through some phase transition. These are 2 different phases. So there must be at least at 0 temperature 1 quantum phase transition at some finite value of U. And numerics, in fact, tells us that there is indeed the simplest picture arising here, that there is a single and continuous transition, a quantum critical point. This quantum critical point defines a new quantum universality class, which cannot be mapped to any classical universality class in some higher dimensions. So it's completely different from the thermal phase transitions that we know at finite temperature, because here we have gapless fermionic degrees of freedom. And this has been studied a lot in the community in the last couple of years, and the transition turns out to be describe a 2+1 dimensional version of the Gros-Neveu field theory. So this is a 2 plus 1 dimensional Gros-Neveu universality class. This universality class is entirely different from what we know from thermal universality classes, even in the characteristic exponents describing this transition. So there is no, although there is no final consensus on the precise value of these exponents, it's very hard to compute. It's clear already now that they're completely different from what would be expected if this were a thermal transition. If this were a thermal transition because it's just SO3 symmetry breaking, we would expect it in the usual Heisenberg universality class. For this universality class, the anomalous dimension would be at least an order of magnitude smaller than what we see here. So the physics of graphene, on the one hand, of course, describes interesting physics that are similar to high energy physics, but it also realizes entirely new, exotic, and I think fascinating emergent phenomena, such as this new quantum universality class. So let me now move on, because actually what I told you about graphene is not the full story. Strictly speaking, at extremely low temperatures, graphene, in fact, is not a Dirac semimetal, but realizes a two-dimensional topological insulator with protected edge modes on its one-dimensional surface. The point is that graphene is, in some sense, in a critical state. It is susceptible to very small perturbations. Graphene is made out of carbon atoms, and carbon is a light atom, so there's weak relativistic effects. For example, spin-orbit coupling is small, but it is finite. Without any spin-orbit coupling, the Dirac cones occurring in the spectrum of graphene would be protected by symmetry. However, now with finite spin-orbit coupling, in fact, a mass gap is allowed. And because it is allowed, it will generically also open up. Maybe small, spin-orbit coupling is small, but it is finite. That changes the picture at extremely low energies completely. There is a mass gap, and turns out that the mass gap is such that the Dirac, the mass at the two Dirac cones is of opposite signs for the two Dirac cones in the Brillouin zone. This, in fact, induces a non-trivial winding of the electron bands, and this non-trivial winding can be explicitly computed by looking at Chern numbers, winding numbers, if you like, that can be computed by an integral over this Berry phase A, which is basically constructed from the wave function here. And for this system, this gapped system, the winding number, in fact, is non-trivial, it's finite. So that means this is a material which has a topological character. And because it's a topological quantity, it's independent of smooth deformations of the bands. And therefore, even if we change a little bit of the bands smoothly, this quantity will not change. On the other hand, the vacuum, that is of course also an insulator, but it's a trivial insulator. The winding number will be 0. Now, if we have a finite system of graphene, then obviously, because in the vacuum, the winding number is 0, in graphene, the winding number is finite, it changes, it must change at the edge from finite integer, say 1, to 0. That can only occur if there is some singularity at the edge. And the only singularity that is allowed is a gap closing. So that immediately tells us that there must be some gap closing at the edge of graphene, of such a graphene sheet. And this, in fact, can also be seen in explicit computations of such a simple model of graphene on a strip. While the bulk of this material has a gap that can be seen here, so this is something that is left over from, say, the first Dirac, and this is left over from the second Dirac. There's a bulk gap. There are bands which sit at the edge and cross at the Fermi level. So there are relativistic edge fermions which sit on the surface of this two-dimensional topological insulator. These edge modes, just as if we included a magnetic, if this were a magnetic field, leads to a quantized conductance. And so the situation is similar to a situation of a two-dimensional electron gas in a magnetic field, a quantum Hall insulator. But remember that here we have not included an external magnetic field. So this is a quantum Hall effect without an external magnetic field. It leads to a quantized conductance because of the edge states. Has this been seen in experiment? Well, not yet in graphene. The thing is that because spin-orbit coupling is small, the gap is also very small, bulk gap, and it's therefore extremely difficult to disentangle the contributions from the bulk and from the edge. This effect, however, has been observed in many systems that realize a stronger spin-orbit coupling. And one of the first experiments, or the first experiments that was done in this respect were performed by the Würzburg group led by Laurens Molenkamp. And it considers an artificial structure, a quantum well heterostructure, a mercury telluride layer sandwiched between two cadmium telluride barriers. So this is again effectively a 2D material, and the influence of spin-orbit coupling can be tuned by growing different sizes of this heterostructure with different thicknesses of this mercury telluride layer. Because mercury is a heavier atom than cadmium, in mercury, in relativistic effects, in particular spin-orbit coupling, is larger than in cadmium. So if we increase the thickness of the mercury telluride layer, then effectively we have a stronger spin-orbit coupling. And turns out that, in fact, in this case, the bands invert, and again, we have a finite winding number. So for large mercury telluride thickness of mercury telluride layers, we have a topological insulator. For small d, we expect a normal insulator because the spin-orbit interaction effects are not large enough. Precisely this expectation is confirmed in the experiment. So here, this graph shows the resistance as a function of gate voltage. With the gate voltage, we can tune the Fermi level through the bulk gap. So here in this regime, this is where the Fermi level is in the bulk gap. And the black curve now shows a sample with small thickness of mercury telluride layer. And that is the sample that is expected to be a normal insulator. And indeed, the resistance increases here up to the experimental detection limit. Note the logarithmic scale here of this plot. However, if we measure samples with larger thicknesses above a certain critical threshold, then in fact the resistance does not increase anymore in this regime where the Fermi level is in the bulk gap, but in fact saturates at this value. And this value is precisely the value that would be expected for a quantum spin Hall insulator. the conductance is quantized at 2e²/h. So these these red and green curves precisely correspond to samples that describe topological insulators. So a two-dimensional topological insulator has one-dimensional gapless edge states. The difference between these two curves is that in these two samples, the width is different. So this quantity W. And the fact that the conductance or resistance in this regime is independent of the width shows again that this is really an effect that comes from the edge states, something that comes from the edge. The bulk is gapped in this material. By analogy, one would maybe then expect that Flatland fermions, two-dimensional gapless edge states, can occur on the surface of a three-dimensional topological insulator. And this is in fact true and can be observed also in a material mercury telluride. So the example is now bulk mercury telluride, so without any heterostructure, no quantum well. If we have relaxed mercury telluride as it occurs in, say, nature, this is a semi-metal. So in fact, there's a quadratic band touching at the Fermi level between the filled and empty bands. These two bands that touch right at the Fermi level with a quadratic dispersion. So this is not yet an insulator, but it can be made insulating by growing the sample on some substrate which has a small lattice mismatch. So by this tensile strain, actually, one breaks the rotation symmetry explicitly and opens up a band gap. Now, is this strained mercury telluride really a three-dimensional topological insulator? It is an insulating material, but does it have gapless edge modes? Now, here's the experiment that should show you that this is indeed the case. This experiment shows the Hall conductivity of this material in a finite external magnetic field. So Hall conductivity as a function of the magnetic field. And the Hall conductivity indeed shows characteristic plateaus at integer values of e²/h. And these integer plateaus are precisely at those values that would be expected for a two-dimensional Dirac electron gas. So that tells us that the effective excitations in this three-dimensional material are two-dimensional Dirac fermions. And the only conclusion that is can be made that is consistent with this observation is that these are surface states that are described by 2D Dirac electrons or on the edge of this three-dimensional material. Of course, that only occurs at room temperature, at least if one strains the material. However, we have recently argued that, in fact, strain is not the only possibility to make out of this mercury telluride a topological insulator, but interaction effects can in fact do the same thing. At very low temperatures, these interaction effects in fact induce spontaneous symmetry breaking, which spontaneously breaks the rotational symmetry in just the same way as what would tensile strain do. So at very low temperatures, cooled, if you like, mercury telluride, the band structure is just the same as what strained mercury telluride at room temperature would have. So at very low temperatures, therefore, there is a transition between the semi-metallic state, mercury telluride, to this three-dimensional topological insulator. So let me summarize this part. Two-dimensional electrons can not only emerge in systems such as flatland graphene, but also on the surface of three-dimensional topological insulators. What is a three-dimensional topological insulator, therefore? On a very pragmatic level, if we think of normal non-topological insulator as just a piece of wood, something that is electrically not conducting, then a topological insulator would be a piece of wood wrapped in some aluminum foil. Of course, this simple analogy is not entirely correct, because the difference is that a topological insulator is just made out of a single compound. And that means that in a topological insulator, the surface has precisely the same chemical structure as the bulk, but still the surface is conducting while the bulk is insulating due to the topology. Let me now jump to a seemingly entirely unrelated branch of condensed matter physics. This is the physics of frustrated magnets. As theorists, we assume these systems, we think of these systems as just the physics of spin models. So one might ask the question whether there are any fermions in the game here. What does this have to do in this talk? In fact, I will now argue that relativistic flatland fermions can arise in this system as a consequence of a very intriguing many-body phenomenon, something that we call fractionalization, with which we mean the emergence of new quasiparticles that have quantum numbers which are just fractions of those original particles, the quantum numbers of the original particles that the material is made of. So what is frustration? Of course, we all know what frustration is, but in physics, frustration refers to a situation in which not all local constraints can be simultaneously satisfied. So consider, for example, three Ising spins sitting on the corners of a triangle, and assume that the interaction between these Ising spins is antiferromagnetic. So each pair of those spins would like to align antiferromagnetically, so in opposite directions. However, if they sit on these corners of the triangle, it's impossible to find a configuration where all those three bonds are antiferromagnetic. In fact, if, for example, those two are aligned antiferromagnetic, then the third one doesn't know whether to point up or down. And in fact, energetically, these two possibilities are entirely equivalent. So this has important consequences when we now think of thermodynamic systems with many particles. If we increase system size and think of, say, just classical spins for the moment, classical spins are just unit length vectors, if you like, then the number of states that minimize the Hamilton function, is in this case, that grows exponentially with system size. So we have an exponentially large ground state manifold with energetically fully equivalent states. Now, this large ground state manifold, of course, is again very susceptible to fluctuation effects, particularly to quantum fluctuation effects. If we think of quantum spin 1/2, for example, represented by Pauli matrices, then in such a situation, small quantum effects will have a large influence. And in fact, turns out that entirely new quantum phases can emerge, something that has no analog in classical physics. And while this idea has been around for quite a while, in fact, only in the last couple of years or a decade, it has been possible to substantiate this enormously because of the presence of exact solutions of particular models. And one most prominent such exactly solvable model is the Kitaev model on honeycomb lattice. And this model I would like to discuss with you now in more detail, because first of all, it's a very important example of an exactly solvable two-dimensional model, but also it features an extremely interesting quantum ground state, a quantum spin liquid that is characterized by new emergent excitations, and these excitations in fact turn out to be fermions and gauge fields. The model itself is seemingly simple, and think of just spin 1/2s sitting on the sides of just such a honeycomb lattice, and we restrict ourselves just to nearest neighbor interactions. The interactions are all Ising interactions. So on each bond, we have an Ising interaction. However, the difference to the standard Ising model is that the quantization axis depends on the orientation of the bond. So obviously, in order to find a material which realizes such an interaction, we need to look for systems that have strong spin-orbit coupling, because here we see already that the orientation in real space is connected to the orientation in spin spaces. So spin and real space are connected. There is no individual SU2 symmetry in spin space anymore. However, in fact, it turns out that there do exist materials which have strong such Kitaev interaction. So what is this Ising interaction? We divide all bonds into 3 different classes, and these are denoted here with the colors blue and green and red. And on all the blue bonds, we have just Ising X interaction. So the quantization axis is along the X-axis in spin space. On the other hand, on the green bonds, and these bonds we will call the Y bonds, we just have Y interactions, so Y quantization axis as Yi as Jy. And on the red bonds, we have that just the Z components of the spin interact. So obviously, this different quantization axis induce some frustration, because it's impossible to satisfy all the local constraints. For example, if you would like to satisfy the blue bonds, we would point the spins just into the X direction. So we would like to maximize the X components of the spin. But then the Z and Y components would not have any energetic contribution, and they would basically be unhappy. So in the end, it's impossible to make all bonds happy at the same time. It's an example of exchange frustration mechanism. This model, surprisingly enough, can be exactly solved. And one possibility is to introduce a Majorana representation of spins. Let me review what I mean with Majorana fermions here. Consider a complex fermion with a creation operator A dagger and annihilation operator A. When considering, in a sense, real and imaginary part of these operators, we can construct new fermionic operators C1 and C2, and this is what I call a Majorana fermion. And this way constructed, these Majorana fermions are Hermitian operators. So creation and annihilation operators of the C are identical, and in that sense, these Majorana fermions are their own antiparticles. They also anticommute as any other fermions, so as they should, being fermions, and they square to 1. fact, we can represent a spin 1/2 in terms of 4 Majoranas, and these 4 Majoranas I call Bx, By, and Bz. And in this representation, 4 Majoranas, the fourth one is actually the C. So these are all 4 equivalent Majoranas, but because C occurs in all 3 components of this representation, I gave this a different name. Bx occurs in the X component, By in the Y component of the spin operator, and so on. So each spin component represented by sigma X, sigma Y, and sigma Z is then represented by a product of 2 Majoranas, and therefore the Hilbert space is enlarged by a factor of 2. That at least can be immediately checked by looking at this Majorana representation. So polymatrices, they act, of course, on a 2-dimensional Hilbert space because these are 2 by 2 matrices. But as can be checked, these Majorana operators, they act on a 4-dimensional Hilbert space. So in order to really have a one-to-one correspondence between these polymatrices and this product of Majorana operators, we need a constraint in this enlarged Hilbert space H tilde. And to this end, we introduce the operator D. D is a product of 4 Majorana operators. D is again Hermitian, it squares to 1, and therefore it has eigenvalues plus or minus 1. And now we select out of this 4-dimensional Hilbert space H tilde only those states for which D is plus 1, so which have eigenvalues D equals plus 1. So D can be thought of as a gauge transformation operator, and in this sense, we select the gauge invariant states out of this larger Hilbert space. So the subspace H then can be considered as the gauge invariant subspace. And indeed, in this physical subspace, the spin algebra known for polymatrices is satisfied by this Majorana representation. Most importantly, the product of the 3 spin components, sigma X, sigma Y, sigma Z, which in general is just I times D, within this subspace where D is plus 1 becomes I as it should be for the components of spins. So in this sense, we have a parton construction. One spin is represented by 4 Majoranas, however, with a gauge constraint, Z2 gauge constraint. This parton construction can be performed, in fact, for any spin model if you like, but usually doing so does not give any progress because we end up then with a very complicated Majorana gauge field theory, and such a model is usually much more difficult to solve than the original model that we started with. However, the situation is opposite in the example of the Kitaev honeycomb model. In this case, it turns out that in fact this Majorana representation makes this Kitaev model extremely simple. So let us apply this representation to this Kitaev Hamiltonian. Instead of having 2 spin interactions, now we end up with 4 Majorana interactions. However, we can combine 2 of those 4 into a product, a new operator that we call U. Because we have included this U, in this U also a factor of I, imaginary unit, this is again Hermitian operator and can be immediately shown that this operator also squares to 1, and therefore it also has eigenvalues plus or minus 1. So this U can be considered as a Z2 lattice gauge field. It lives on the links, has two indices, I and j, between the sites I and j. Most importantly, these U's commute with the Hamiltonian and can also commute with all other U's, so among themselves. So it's possible to simultaneously diagonalize the Hamiltonian and all U's at all links at the same time. So in a sense, we can simply remove the head of this U operator and end up with just eigenvalues Uij. And these eigenvalues are just plus or minus 1. So the Hilbert space separates into sectors in which these U's are just plus or minus 1. And within such a sector, we end up with just a Majorana hopping problem in the background of a static gauge field. So in this representation, the microscopic degrees of freedom of this model, the spins, fractionalize into new emergent quasi-particles, Majorana fermions that interact via static Z2 gauge field. So what's the ground state then of this system? In fact, one can show that the ground state is translationally invariant, and without loss of generality, we can then assume that all these U, the link variables, are just plus 1 in the ground state on all links. The ground state describes a quantum spin liquid, and in this case, it's a Z2 quantum spin liquid. A quantum spin liquid is a state that is described by a gauge field theory, characterized therefore by fractionalized excitations. And in this case, it's the fermionic Z2 gauge field theory. The spectrum of these fermions can be either gapped or gapless, depending on the parameters of the model. And these are these three spin-spin interactions, if you like. In the isotropic case, where all these three parameters, k parameters, are equal, then we're in the so-called B phase, where again we have gapless fermions. So these are gapless Majoranas with relativistic dispersion relation, say Dirac cones. And in that sense, this phase describes now a fractionalized version of graphene. Graphene made out of fractionalized excitations. Very intriguingly, in fact, the gap in this phase can also be opened up by simply applying an external magnetic field, something that is basically present in any lab. In this case, it turns out that the spectrum is topologically non-trivial, the winding number is non-zero, and therefore also this fractionalized version of graphene, when the gap is opened up, has a spectrum with gapless edge modes. So the isotropic Kitaev model in an external magnetic field is then a fractionalized version of a two-dimensional topological insulator. And such behavior should have characteristic signatures in transport experiments. Can such a behavior indeed be seen? Well, right now we do not have the perfect material that realizes the Kitaev model. However, alpha ruthenium trichloride seems to be very close to it. Alpha ruthenium trichloride is a layered mod insulator with strong spin-orbit coupling and has been argued to realize strong Kitaev interaction. The ground state of this model without an external magnetic field is, however, magnetically ordered, but so this is not a quantum spin liquid without an external magnetic field, but the order can be suppressed by applying an external magnetic field. So in this case, there's at least the possibility that there may be some topological mod insulating ground state upon applying magnetic field. However, how can we detect it in experiment? Because the Majorana fermions are not charged under our physical U1 gauge field, our electromagnetic field, their characteristic plateaus are only observable in heat transport measurements, not in the usual charge transport measurements. And here you see an experiment that was done recently showing the thermal Hall conductivity as a function of magnetic field. And precisely in the regime where the magnetic order is suppressed, we observe that this thermal Hall conductivity saturates at value that is precisely half of what would be expected for Dirac fermions. So this is precisely the value that would be expected for Majorana fermions, because Majorana fermions are in some sense half of complex fermions, Dirac fermions. So if this experiment is indeed confirmed by other groups in future, then this would indeed be a smoking gun signature for Majorana edge states in this material. How about interactions? Can we also observe some fractionalized version of of the new quantum universality class that we have seen in interacting Dirac semimetals, so interacting graphene? In fact, for simple Kitaev, the usual original Kitaev model, this turns out to be extremely complicated. The reason is that once we add any other interactions, such as, for example, simple Heisenberg interactions, this not only induces short-range interactions of the Majorana fermions, but also interactions from the Majorana fermions with the gauge field in the way that the gauge field is no longer static. And once we have now a fluctuating gauge field theory, this is extremely complicated to handle theoretically. There are no quantum Monte Carlo simulations possible because of sign problem issues, and any other analytical approaches are extremely difficult. So therefore, in order to find systems that could, in principle, realize fractionalized version of fermionic quantum critical points, we have to generalize the Kitaev model a little bit. And in fact, this is perfectly possible by allowing more degrees of freedom. And such degrees of freedom are not unphysical if we think of materials that have, for example, not only spin, but also orbital degrees. And in this case, for example, in such a Jacobs 3/2 system, we have 4 states which are degenerate: spin, up and down, and the orbital, if you like, up and down. And in fact, the Kitaev model can be generalized by replacing these sigma matrices, the spin 1/2 matrices, by gamma matrices. So higher dimensional representation of the Clifford algebra. And in the simplest case, these would be just 4x4 matrices. So in the simplest generalization, describing this doublet of such a spin orbital model. And let me look at this example a little bit more in detail. So now we would like to represent again these 4x4 gamma matrices by Majorana fermions. And so in the same way we did this for the Kitaev model, we can do it also here, but now we need to have 5 B fermions because there are 5 anti-commuting 4x4 matrices. Then we again have the C Majorana fermion. So in total, we will have 6 Majoranas, and that need to be distributed on some lattice. So for example, on the square lattice, we can define a generalization of a Kitaev model, a Kitaev spin-orbital model, where on the square lattice, each neighbor has 4 bonds, each site has 4 nearest neighbors, and therefore 4 of the 6 Majoranas are bound into this static gauge field, the U operators. And this leaves now 2 itinerant Majorana fermions. So this is now a model which has 2 itinerant Majoranas. And we can also do the same thing also on honeycomb lattice. On honeycomb lattice, each site has 3 nearest neighbor. It's a 3-coordinated lattice. And therefore, only 3 out of the 6 Majoranas are bound into the gauge field operators. And this leaves us with 3 itinerant Majorana fermions coupled to the Z2 gauge field. Let me focus on this example a little bit more. In this case, in fact, we can add another interaction to the Kitaev interaction, which induces the Kitaev spin-orbital liquid in this case. And this interaction, this further interaction can, for example, be just a simple Heisenberg interaction. A Heisenberg interaction among the spin degrees of freedom. So the spins here are represented by sigma and the orbitals are represented by the tau operators. This interaction can be shown to induce 4 Majorana interactions, but still leaves the Z2 gauge field static. And this means that for small j, we still have a Kitaev spin orbital liquid described by 3 itinerant Majorana fermions coupled to a Z2 gauge field. But at very large j, these spins would like to order, and if j is positive, then they would like to order antiferromagnetically. So we have a spontaneous symmetry breaking in the spin sector and some Néel type of order. And therefore, there must again be a transition between these 2 different phases, at least one transition as a function of j. The simplest case would be that there is a single transition, and in fact, this expectation is indeed confirmed by the DMRG calculations, which substantiate this picture. And turns out that there is a single continuous transition from the spin orbital liquid to this Néel ordered state. This transition is described by gapless Majorana degrees of freedom, and therefore describes a fractionalized version of a 2+1 dimensional Grosne-Neveu transition. So what is this fractionalized 2+1D Grosne-Neveu? This is a Grosne-Neveu transition between topological phases, and therefore we may dub this a Grosne-Neveu star transition, a terminology borrowed from the Ising star transition, Ising transition between topological phases. What are the differences of Grosne-Neveu star versus Grosne-Neveu? The adjacent phases are topological, and therefore there are different states in the spectrum that can indeed be observed in finite size computations. So because of the topological character of the adjacent phases, we have 4 topological sectors occurring in the spectrum at this quantum critical point. But because of the gauge constraint, which disallows non-gauge invariant states, also some other states that occur in the usual Grosne-Neveu spectrum will be missing in the spectrum of Grosne-Neveu star. So these are universal fingerprints that should be observable in finite size spectra, for example, on the torus at this quantum critical point. The quantum critical point is towards Néel order, but even without this topology, the field theory describing the transition is different from the usual Grosne-Neveu Heisenberg, the chiral Grosne-Neveu transition, chiral Heisenberg transition. And the reason is that the order parameter here in this case transforms as a fundamental of SO3 instead of the fundamental of SU2. So this matrix here, L, is not a spin 1/2 matrix, it's not a poly matrix, but it's a spin 1 matrix. And therefore, this field theory describes a new member of the Gros-Neveu family, and we call it the Gros-Neveu SO3 field theory versus the Gros-Neveu SU2 field theory, which would be the Carl-Heisenberg field theory. The field theory therefore also has different exponents, and we have estimated the critical exponents characteristic for this new universality class using leading order large N and epsilon expansions. So let me conclude. I've shown you 3 examples for intriguing new physics that emerges from the interplay of many particles. I've shown you an emergent symmetry that can be realized in systems such as graphene, also topology that can emerge in systems that have a non-trivial winding of the electron bands. And maybe most intriguingly, there can even emerge new types of particles, in this case, fermions that arise as a consequence of a non-trivial interplay in a model of just spins. Surely, all these phenomena in principle are fully described by good old non-relativistic quantum mechanics. But as Anderson said, more is different. Or maybe as in the purported conversation between Fitzgerald and Hemingway, you know, Ernest, the rich are different from you and me. Yes, they have more money. Thank you for your attention.